This video is on thermodynamics, and we're going to be looking at thermodynamics and the two components that help us through thermodynamics to determine if a reaction is thermodynamically favored. So the first thing we need to talk about are the laws of thermodynamics. When we were covering thermochemistry, we talked about the first law of the conservation of energy, that energy is not created or destroyed. In this part of the unit, we're going to be focusing mostly on the second law, which is the universe is constantly increasing in disorder. So to remember that, we can just focus on the fact that chaos rules, and we talk about the universe is constantly expanding, and things are always getting more disorderly. Think about your room, think about your desk, think about your life. Unless you pick everything up and put it back in order, it's always getting more disorderly. I'm going to talk about the third law real quick. The third law says the entropy, or the disorder, of a perfect crystal at 0 Kelvin is 0. So that's going to come into play when we start talking about states of matter. But we hardly ever have an entropy value of 0. And we don't know what entropy is yet. We're about to talk about that. But the only time you have an entropy value of 0 is when you have a perfect crystal at 0 degrees Kelvin. So just keep in mind when we start talking about entropy values, like we talked about enthalpy values, entropies are rarely 0 and they're always positive numbers. We didn't have that when we were talking about enthalpy values. So what is entropy? Entropy, the symbol for entropy is delta S, and delta S is a measure of the disorder or randomness of a system. More disorder is favored. Nature tends towards chaos. That's the second law of thermodynamics. So if a system is getting more disorderly, then the entropy is increasing. And increasing means it's going to have a positive value. So if a reaction is getting more disorderly, then the entropy, or the delta S value, is going to have a positive. If the reaction is getting less disorderly, then the entropy is going to decrease, and that means the delta S is going to have a negative value. So just keep in mind, if it is getting more disorderly, then the entropy is increasing, and the sign of delta S is positive. If it's getting less disorderly, the entropy is decreasing, and that means the sign of delta S is negative. Just a note, we don't say that it's getting more disorderly or more orderly. We just refer everything to the term of disorder. So you're going to get more disorder or less disorder. I know that sounds like a double negative, but the definition of entropy is a measure of disorder, so we're going to keep referring to that. So predicting the signs of entropy. So we're going to look at reactions and decide if the reaction is going to get more disorderly or less disorderly based on what's happening in there. So this is temperature dependent because increasing the temperature or the volume can lead to independent movement of particles. The system will have more disorderly as temperature increases, therefore having a positive entropy. By looking at the phases within the reaction and what's happening in the reaction, we can actually predict the sign of the entropy. So here's a couple of general rules that we can follow when we are looking at predicting the sign of the entropy, or deciding if the reaction is getting more disorderly or less disorderly. First, we can look at states, okay? Because we have to look at the particle arrangement, and the least disorderly arrangement of particles is in a solid, and then getting more disorderly goes to a liquid, and getting even more disorderly goes to a gas. So gases are the most disorderly states, and solids have the least disorder when you're comparing those states. The other things that we can look at is liquids or solutions formed from solids. So really, if we are going from a solid to an aqueous solution, so like dissolving a salt, getting more disorderly, aqueous is more disorderly than solids. The last thing we can look at is the number of gas molecules in the reaction. Okay, so if we look at the reactant side and compare it to the product side, and we see that there are more moles of gas on the product side, well, that means there's more disorder. So if you compare the moles of gas on the reactant side to the moles of gas on the product side, that can help you decide if it's getting more disorderly or less disorderly. So a little bit of practice. Let's look at these reactions and decide, is the disorder increasing or decreasing, and what's that mean for the entropy? So first reaction, we have carbon dioxide solid going to carbon dioxide gas. Well, where's the more disorder? The more disorder is in the gas. So what can we say? The disorder is increasing, and therefore this reaction, delta S, is positive. Second reaction, we have calcium oxide reacting with carbon dioxide to make calcium carbonate, and we are going from a solid and a gas to just a solid. So what's happening there? We're getting a more organized product, and that means what's happening to the disorder? It is decreasing. And so what does that tell us about the delta S, the entropy? The delta S is negative. Next reaction, we have a gas going to a gas, and they are going to a liquid. So what's happening to our disorder? We are decreasing, and so delta S is negative. Last one, we have gas to gas. So we can't really look at changes in state because they're all the most disorderly state. So what about the moles of gas? So on the reactant side, we have 3 moles of gas, and that is becoming 2 moles of gas. So what is that doing? The disorder is decreasing because we have less moles of gas, and therefore the delta S is negative. And there's your answers in case you wanted to check that. So what about calculating entropy values? Well, because the third law of thermodynamics establishes a 0 point for entropy, values for entropy can be experimentally measured. So it's temperature dependent. The standard entropies of elements are not 0. Because if you think about it, an element, even if it's at room temperature, is going to have some disorder to it. So think about water at room temperature. It's not the least disorderly state at room temperature. At room temperature, water is a liquid, and that has some disorder to it. So you're not going to see 0 values for entropies. They're all going to be positives for when you're looking them up on the table. We can use those on a table, specific entropies for specific elements or compounds, and calculate the entropy of a reaction by using this equation. This equation is on your equation sheet. You've seen it before. You should know how to use it. The entropy of the reaction is equal to the sum, that's what the sigma means, of the entropies of the products minus the sum of the entropies of the reactions. So just like we did before with enthalpies, we're going to do the same kind of calculations with the entropies. You'll be given a table of entropies, and you'll be able to use those to calculate. And don't forget, coefficients matter, just like we did when we did the enthalpy calculation. So let's look at a reaction. So here's our reaction. We have sulfur dioxide plus oxygen is making sulfur trioxide, and they're giving us the values of each of the entropies for each of these. So let's do the calculation. So start plugging it in. Delta S is equal to the sum of the entropies of the products. Well, sulfur trioxide, there are two of them, and the entropy of sulfur trioxide is 256.6, and that's our only product. Minus reactants, sulfur dioxide, we have two of those, and it is 248.1. Plus the oxygen, we have one of those, that's 205.3. And type all of those things into your calculator, and you're going to get an entropy value of negative 188.3. Units are joules per mole Kelvin. All right. And does that value make sense? Well, if you look at this, that negative value says that this is getting less disorderly. And does that make sense? We'll look at our reaction. We are going gas, gas to gas, and we are going 3 moles of gas to 2 moles of gas. So we could have predicted that this was getting less disorderly, and that would give us a delta S that was negative, which is in fact what we found. So double check and make sure that your calculations make sense based on the reaction. And you should be pretty good at this since we did a lot of this with the enthalpy calculations. Same way. All right, next practice problem, practice number 2. I'm giving you a reaction and I want you to calculate the enthalpy and the entropy of the following reaction. You'll see this a lot. So they give us the delta H values and the delta S values, and they ask us to calculate the H's and the S's. So we're going to do it exactly the same way as we did before. We're going to use the enthalpy of the products minus the reactants to get the delta H value. And we're going to use the entropies of the products minus the reactants, and we're going to get the delta S values. So really it's just plug and chug into the reaction, or into the equation, and see what you get. So delta H values. Delta H is equal to products 2 times negative 826 minus reactants 4 times 0 plus 3 times 0, and that gives us a value of negative 1652 kilojoules per mole. Delta S values, same deal. We're going to do 2 times 90 minus 4 times 27 plus 3 times 205. Plug that into your calculator. Delta S is equal to negative 543 joules per mole Kelvin. There's your work, in case you want to go back and look at it. Now the question is, does this make sense? Does the fact that my entropy value is negative 543 joules per mole Kelvin? Well, look at our reaction. We are going from 4 moles of a solid, 3 moles of a gas, to 2 moles of a solid. What's happening to our disorder it is getting less disorderly, and therefore the sign of the entropy should be negative, which is exactly what we found. A couple of final notes on entropy. There's another way to calculate entropies. Every once in a while we see this, not very often, but you can calculate entropies using the stepwise process. So being given multiple reactions and you have to fit them together to the overall reaction, that will allow you to get the entropy values. Again, it's one of those things, if you reverse the reaction, well, then you just flip the sign of the entropy. If you have to change the coefficients, then you're going to multiply the entropy so that the sum of the steps equals the overall. So you could possibly have a stepwise way to calculate entropies. The other thing I wanted to make sure we talked about was the units. The units for entropy are joules per mole Kelvin. There's a couple of reasons for this. Number one, just like enthalpy, it's per mole of reaction. So it's the amount of energy per mole of reaction. But because the reaction, or the states of the things in the reaction, are temperature dependent, and because entropy is temperature dependent, you see that Kelvin in there. Because temperature can impact the disorder of a compound, the unit requires a temperature component. We're going to come back and have to deal with that in the next part. So I just wanted to make sure that you paid attention to the units. The units are joules per mole Kelvin. And the fact that entropy values are in joules will become a problem when we have to start putting enthalpy and entropy together. So just be really, really aware of the fact that it's joules for entropy usually, and that Kelvin is the unit that your temperature is going to be in.